qui est en en Inde. Ensuite, Margot VULLIEZ, qui nous vient de Poitiers, de l'Université. Et donc, moi-même qui suis de l'Université de Toulouse, et Damien CHABLAT, qui est le directeur de thèse. Donc, nous allons vous écouter, je pense que c'est 40 minutes. On n'a pas évoqué, à peu près, hein, pour vous donner un ordre de grandeur. Suite à quoi nous vous poserons les différentes questions. Enfin, on écoutera vos rapporteurs et on passera à la séance de questions. Voilà, donc la parole est à vous. Je vais demander aux membres du jury de couper les micros, si ce n'est pas déjà fait, de façon à ce qu'on n'ait pas de retour. Et donc, Swaminath, on vous écoute.
Merci beaucoup Pierre et merci tout le monde. Alors, je vais passer ma parole en anglais. J'espère que ça va aller pour tout le monde. So, good morning everyone. I'm Swaminath VENKATESWARAN. So, I'm here to present my PhD defense on design of a bio-inspired robot for inspection of pipelines. So, this will be the outline of today's presentation. So the thesis begins initially with preliminary work, which covers the state of the art and some mathematical concepts that will be covered for the thesis. Followed by that, it will be the phase 1 of thesis, which concentrates on a case study of a robot developed at LSU in France. And then it will be phase 2, which concentrates on the proposal and analysis of an articulation unit. And then finally, phase 3 concentrates on the prototyping of an articulation unit and also the design of optimal robot design. And finally, the thesis ends with conclusion and future perspectives. So generally, robots have an important application in industries such as automobile and manufacturing because they not only reduce human effort, but also does the task with better accuracy. So even in industries such as nuclear, chemical, and sewage, inspection robots play an important role for pipeline because they can do the task with accuracy, but also reduce long-term radiation effects or even reduce the loss of human life. So generally, the architecture of a piping inspection robot comprises of a head, a platform, and a cable, which are represented here. So basically, the head consists of the device such as a camera, and the platform houses all the equipments of the robot. And finally, the cables, which are used to transfer information from a central control system to the current position of the robot. So in general, a piping inspection robot is encountered by several scenarios such as a diameter variation, a 90-degree bend, a 45-degree bend on elbow, a T-union or a junction, or even the presence of deposits. So these inspection robots are associated with problems, namely movement inside pipelines, like how accurately it's being positioned on the given zone, and inspection of the desired zone, or even intervention on the desired zone by withstanding the load of the mounted devices. So this thesis will mainly concentrate on addressing the first issue, which is associated with the movement. And also this thesis will look for the design of an inspection robot for diameters less than 150 millimeters that can adapt its structure to overcome scenario A and also potentially overcome scenarios B to D, such as bends and junction. So generally, the locomotion techniques of piping inspection robots can be classified via pig type, wheel type, ball press type, or even screw type. And another interesting classification was proposed by Kasim via mechanical and bio-inspired locomotion systems. So basically, mechanical systems are locomotion systems employ mechanical elements for accomplishing the locomotion or to have contact with the walls of the pipeline. Some examples include a wheel type system that uses wheels to have contact with pipeline walls, or a track type system that uses a conveyor system with pulleys and rollers to have contact with pipeline walls, or a helical type system which exploits the screw motion to move along, to translate along a given pitch and move inside a pipeline, or a flexible feed system which uses a piezoelectric biomorph to accomplish locomotion inside a pipeline. And then we have bio-inspired systems, as the name indicates, locomotion techniques inspired from nature, such as animals. So these are more or less connected to mechanical systems because they require mechanical elements to accomplish the given locomotion of an animal. So some examples include a worm type system, which can be a caterpillar or an earthworm. And then we have a snake type system, which exploits the locomotion of a snake by using multiple actuators to move in a given environment. Or even we have a spider type system that has legs to have contact with pipeline walls or a given environment. And then we have gecko type system, which exploits the van der Waals force of attraction to have or stick to a given surface or a given pipeline wall. And then we have something called articulation units, which is basically a mechanism that can permit to have a reconfigurable or flexible system. And they assist assembly of rigid bodies to move to the desired position by adapting the entire structure. So these are some of the examples. We have a universal joint, which is quite commonly found in robot manipulators or even piping inspection robot where it's actuated. And it can help the assembly to overcome a pipe bend at 90 degrees or pass through a junction. And then we have a passive example like spring, which is used to bend the entire robot assembly to overcome a pipe bend at 90 degrees, for example. And then we have a flexible system, which is like the spring, but with higher load carrying capacities. It can be a flexible bearing or a flexible sleeve coupling. Again, a passive solution to overcome a pipe bend or a junction. And then we have another interesting example, which are tensegrity structures that employ bars in compression and springs in tension. They are basically lightweight mechanisms which can manipulate in a given environment or overcome an obstacle. And also this thesis explored some of the mathematical concepts such as singularity analysis of parallel mechanisms and application of algebraic tools such as cylindrical algebraic decomposition, which is CAD, the Grobner-based elimination technique for the analysis of workspaces and singularities, and the methods of tilt and torsion theory and Euler transformation matrices for geometric construction of mechanisms. And then the Siropa library of Maple, which is a powerful library developed for the design, analysis, and simulation of parallel mechanisms. And eventually some MATLAB optimization techniques for optimal design of mechanisms and robot assembly. So moving forward, the phase one of the thesis concentrates on a rigid bio-inspired piping inspection robot, and it tries to address the following question, like how can a locomotion be accomplished inside a pipeline? And what are the forces required to have a good contact with the pipeline walls? So in this context, a rigid bio-inspired piping inspection robot that moves like a caterpillar was developed as a part of a research project back in 2014 at LS2L. So by using leg mechanisms and DC motors, the robot accomplishes the locomotion of a caterpillar in six steps. As you can see, a small simulation here. The problem is that the robot is a rigid model and it cannot be used for pipelines having bends and junctions. And also the velocities of the motors used are pretty low. And also force models, namely static and dynamic, were not studied, and also experimental validation were not carried out. So the last 2 points will be addressed in this phase of thesis. And so these are the representation of the various modules on the digital model of the robot. We have rear and front leg modules, which comprise of 3 legs at 120 degrees out of phase, and they try to establish contact with walls of the pipeline. And then a central module, which takes care of elongation and retraction, and eventually to arrive at the locomotion of a caterpillar. And so this is the architecture of the robot inside a pipeline of radius R, for example. And by using a multi-objective optimization approach, the optimal dimensions of the slot follower leg mechanism was determined that employed the inverse kinematic problem of the leg mechanism, and also the force transmission factor, which is used to create relation between the actuator forces and the contact forces through the Jacobian. So moving on to the force models. So basically static and dynamic force models are developed for this robot. So generally, when the robot is under locomotion, we can have 2 types of models. First one is called the model A, where the rear leg mechanisms are clamped to the pipeline wall and the front end is free, and the vice versa with model B. And when one set of leg mechanisms establish a contact with the walls of the pipeline, we can have 3 sets of forces at each point, which are the normal forces, the radial forces, and the longitudinal forces. And apart from that, some important orientations have been taken into account, such as the orientation of robot about its own axis, and also the rotation of pipeline about the x-axis, which is denoted by delta. So for the static force model, we begin with something called a wrench model, which comprises of the force vector and the moment vector. Basically, the force vector consists of the radial forces and the longitudinal forces. And for estimating the torques at the central point, we use the Wagnon's moment transport rule, which states that the total moment acting at a point is equal to the sum of moments at each point. And then we estimate the normal forces, which are nothing but the contact forces, based on Coulomb's law of dry friction, using the radial and longitudinal forces and the coefficient of friction between bronze legs and steel walls of pipeline. And eventually the actuator forces are estimated using the relation of the force transmission factor, which is shown here. And then we have the dynamic force model, which are used to estimate the forces on the actuators and the locomotion. So the initial analysis was done by Frederick Boyer by incorporation of the recursive Newton-Euler algorithm. And this is the general representation of the various body parts of the robot, which comprises of around 29 bodies with non-zero masses, active links, passive links, and some clampings. And this is a bill of materials used, for example, steel material for the actuators, bronze for the legs, and copper for the cables. So similarly, we have a velocity component equation in dynamic force model, which is a function of the homogeneous transformation matrix. And then we have a wrench model, which comprises of the forces and the moments that are function of the inertial matrices. And eventually the motor torques are computed using the wrench model as well as the Coulomb and viscous friction parameters. And moving forward to the results, the longitudinal and radial force equations are estimated using software such as Maple. And for the simulation, we consider a straight pipeline with two diameters, 54 and 74 millimeters. And here W indicates the self-weight of the robot, which is measured from CATIA by not taking into account the weight of the cables. So as I said earlier, when one set of leg mechanisms have a contact with pipeline walls and the other end is free, owing to the self-weight of the robot, a moment is being induced at the fixed end. And this moment is usually caused by the self-weight of the robot, which is at a distance of the center of gravity from the clamped end. So we can have four possible configurations of the CG position, which are measured from CATIA as a function of the diameter of the pipeline, and also as a function of the position of the central actuator, which can be either fully extended or fully retracted. And we also calculate the force transmission factor for the two diameters considered, which is 54 and 74. And for the results of actuator forces, for the smallest diameter pipeline, when the orientation is vertical, the forces are almost constant and pretty low because it's only the radial forces that exist, and the longitudinal forces do not exist because they depend on the orientation of the pipeline. Whereas if the orientation is horizontal, the highest amount of force was measured on the central actuator extended position of around 70 Newton. And we can observe a variation of this force. It's because of the orientation of the robot about its own axis, which can go from 0 to 2 pi radians. And the highest amount of forces were observed on the 74 mm diameter pipeline. It's because it depends directly on the force transmission factor, and the values are on 120 newtons. And then moving forward to the dynamic force model, a trajectory planning is performed using the fifth degree polynomial equation to arrive at the displacement, velocity, and acceleration profiles. So the total time taken for the simulation is around 5,500 seconds, owing to the low velocity of motor units, which is around 0.43 millimeters per second, and eventually very low values of acceleration. And then we have the results of forces on each actuator under locomotion. For example, for model A, when the orientation is horizontal, the forces on the central actuator are pretty close to 0. However, the leg actuator forces are range between -4 to 4 newtons. It's the same case for model B when the orientation is horizontal. However, in case of a vertical orientation of pipeline, the central actuator forces are pretty much on the higher side of around 8 Newton, which is mainly caused due to gravity. But in the case of model B, the forces on the central actuator was around 10 Newton. It was mainly caused due to the presence of umbilicus that imposed a slight load on the robot. However, the leg actuator forces remain the same irrespective of the orientation of pipeline for the dynamic force model. So to compare, the static forces were found to be pretty much higher than the dynamic model, which was mainly due to the low velocity of the motor units and low inertia of moving masses. However, the dynamic model helped in identifying what are the forces on the central actuator, which was not possible in the static model. And then the static force model are then used as inputs for accomplishing clamping phases during the experiments. So when then the prototype of the robot was realized by assembling the DC motors, servo controllers, fasteners, and connecting elements. And then an interfacing was being done between the servo controllers and the motors using a BeagleBone Black microcomputer, where a force control algorithm is written to apply duty cycles with the help of PWM and GPIO cycles. And we apply something called a threshold to attain static clamping phases during the locomotion. So the experiment was carried out inside a 74 mm straight pipe, which is of transparent PVC material and of 2.5 meters long. So initially the output voltages were measured from ADC and sent to the user, from which we can calculate the current. And it was observed that a lot of noises were there. It was mainly due to the numerical errors associated with the BeagleBone Black card and also some frequency issues. So that's using a filtering technique called Savitsky-Golay, which uses a least square approximation to smoothen signals without distorting them, was employed to reduce the noises. And with the current data, we can estimate the torques and the forces based on the relation with the torque constant. And the spindle drive forces were estimated for horizontal and vertical orientations of pipeline. And it was found that at the starting and ending of each phase, higher forces were observed. And it was mainly because a constant velocity profile was employed in the control law. And also some slightly higher forces were observed in the vertical orientation of pipeline, which was mainly due to the effect of gravity. And using the actuator forces, we can calculate the clamping force based on the relation with the Jacobian matrix. And it was found to be around 630 newtons, which was pretty much higher than the static model. And this is a small simulation of the digital model and the experiments. So above you can have the digital model simulation in CATIA, and at the bottom, the 6-step locomotion of the robot inside a pipeline. So 2 forward motions are being completed and then 2 reverse motions so that the robot returns back to its initial state. Okay. So to conclude, this phase concentrated on the implementation of force models for the bio-inspired piping inspection robot. And then validation of experiments on the prototype was carried out using simple electronic devices. And then some factors were identified that caused deviation between the numerical and experiments, which were mainly due to electromechanical and frictional effects, which were not possible to be considered in the numerical model. And then it was also possible to identify a robot which can potentially operate within a pipeline having diameters less than 150 millimeters. And below you can see some contributions at the end of this phase. So moving forward to the phase 2, it concentrates on the design and analysis of a tensegrity mechanism, and it tries to address the following questions, like what are the issues to be addressed to overcome a pipe bend and junction, and what is the design of an articulation unit that can have a stability and also considerable tilt limits. So as I said earlier, the problems with the existing prototype, it's rigid, cable management issues were not addressed, and also low velocity. So in this phase, we try to address the issue of rigidity by converting the system into a flexible system by the design and analysis of an articulation unit. So before going into the design, there are some factors that has to be considered for overcoming pipe bends and junctions. The first one is called the passive compliance, which could be imagined for a robot that has to pass through a pipe bend at 90 degrees and where it is essential for the articulation unit to be in a passive mode. And then we have the active compliance, which could be imagined for a robot that has to pass through a T-union or a junction, and where the articulation unit must be necessarily actuated. And then we have the tilt limits, the maximum angle up to which the robot can bend, the articulation unit can bend to overcome a pipe bend or a junction. So the existing architecture of the robot is modified into a reconfigurable version, a flexible system by incorporation of the articulation units between each module, and also a 4-bar wheel mechanism was proposed to be introduced on the front and the rear end of the robot, which can potentially assist the robot to enter and exit pipe bends smoothly. So by taking into account all these factors, a tensegrity mechanism that employs 3 tension springs and a universal joint was proposed as an initial solution for as articulation unit for the bio-inspired robot. So under passive modes, the mechanism will operate autonomously to overcome a 90-degree pipe bend. In the case of active compliance, cables that pass through each spring of the mechanism can be actuated to tilt the platform of the mechanism to overcome a pipe bend or a junction. This mechanism is correlated to a 3-SPSU parallel manipulator to arrive at the geometrical equations, and two analyses are being carried out. The first one uses the theory of tilt and torsion to analyze the joint limits, and the next one concentrates on the study of singularities and workspaces for the Euler angles of the universal joint. The first concept concentrates on the theory of tilt and torsion, which is employed in parallel kinematic machines where the mobile platform is usually asymmetric. So by projecting the tilt and azimuth angles of the universal joint, the transformation matrices are determined. And since we have a parallel mechanism, the inverse kinematic problem is pretty much simpler, which is used to map the base to the end effector by using the distance relations. And so these are the results of IKP for the theory of tilt and torsion. So for the positioning of the end effector about the central axis of the universal joint, it is affected by the value of parameter gamma. So based on which we can have three case steady postures. The first one is called the pendulum, where the value of gamma is less than 0 or negative. The next one is called the neutral posture, where the value of gamma is 0. And the next one is called the inverse pendulum, where the value of gamma is greater than 0 or positive. So for the analysis of this mechanism, we use the Siropa library of Maple to create the manipulators, transformation of inverse kinematic problem into constraint equations, and extraction of feasible workspaces using CAD. So CAD is basically an important tool that is employed for symbolic computations in the field of engineering and mathematics, and it comprises of decomposition of space into collection of cells and projection of each cells for a given variable, and where each cell is described by a set of polynomial equations. So for parallel mechanisms, they are used to study the feasible workspaces and also isolate the singularity aspects. So the constraint equations are transformed into inequalities using Siropa by setting joint limits that go from 7 millimeters to 31 millimeters. So these are the results obtained. So here the blue color represents the feasible solutions, and white regions represent solutions which cannot be which are not possible. So as you can see around the home post, we have some solutions and also some white regions and some solutions beyond the white regions. So generally it's difficult for the mechanism to attain the solutions beyond the white zone, as it has to cross some singular configurations. So we just isolate the solutions concentrated about the home post. So for the pendulum configuration, if you see, the value of alpha is around plus or minus pi by 18 radians, which is very narrow. However, in the case of neutral post, the results are considerably better, and it is around plus or minus pi by 6 radians. And then in the case of inverse pendulum configuration, the results are even more better, and it is found to be around plus or minus pi by 3 radians. So we just stick with the inverse pendulum configuration for further analysis. So this is a small simulation of the theory of tilt and torsion on the three configurations. So as you can see, a tilt is applied, an azimuth from 0 to 2 pi to have a complete rotation. And once again, another tilt and an azimuth to rotate the mechanism. So since an inverse pendulum configuration was chosen, so by nature, the inverse pendulum is unstable. So in order to ensure that we have a stable configuration, stability analysis must be done, for which the Lagrange equation of motion is used under static modes. So under static modes, it's only the potential energy that exists, and it is mainly contributed by the presence of cables and the springs. So in order to have a stable condition, the second order derivative of the potential energy, or which is also called the mechanism stiffness, must be positive. So initial analysis was done by considering fixed design parameters, such as the value of H was fixed at 1, and it was found that an unstable configuration was obtained. So for finding the stable configuration, the second order derivative of potential energy is studied at the home post, where the tilt angles are 0. And a trace is being created between the mechanism stiffness, the parameter H, and the value of RF and values of RF. And the value of H 0.5 is chosen from the trace where a stable configuration could be potentially obtained. And then the workspace analysis is re-verified, and it will be seen that the tilt limits are considerably reduced from pi by 3 to pi by 6 radians. But the advantage is that if we have no preload, we can have a stable configuration. And if we have a preload of 2 Newton on each spring, we can also have a stable configuration. So since the tilt limits are considerably reduced, one solution could be to go for a stack model, if in case it's implemented for the bio-inspired robot to overcome a pipe bend at 90 degrees or even a junction. And the theory of tilt and torsion gave an insight about identification of case study postures, but to really study the workspaces, the singularities must be verified. So which has to be done for the Euler angles of the universal joint. So since we have a parallel mechanism, we can have the possibilities of three types of singularities. The first one is the type 1, which can exist when the inverse Jacobian matrix, the determinant becomes 0. Or a type 2 singularity when the direct kinematics matrix determinant becomes 0, or type 3 when both the determinant of the matrices become 0. So since the 3-SPSU mechanism has 3 joint variables and 2 articular variables, which do not yield a perfect square matrix, the mechanism is split into 3 sets of 2-SPSU architectures for analyzing the singularities. So type 1 singularities can only exist if one of the lengths of the prismatic springs becomes 0, which is not possible. However, type 2 singularities can exist when one of the design parameters or the tilt angles can become 0, which is highly possible for this configuration. So by setting joint limits and creation of the inverse kinematic problem, they are transformed and set as inequalities for CAD algorithm. And initial joint limits were set at 10 to 30 millimeters, from which the regular workspace, which is in the form of a triangle, is extracted, which led to the modification of the joint limits to 13.5 millimeters. And the regular workspace, which is in the form of a triangle, is extracted, and it will be seen at the bottom right. The problem is that if the mechanism is allowed to operate autonomously on the singularity boundaries, there are chances that it can drop into singular configurations. So the regular workspace, the safe zone, is usually in the form of a square, which is extracted from the workspace region. And the tilt limits are found to be around plus or minus pi/6 radians, which are considerably smaller. And so thus, this architecture is ideal for addressing the issue of active compliance, but maybe not suitable for the issue of passive compliance. So since we have very narrow tilt limits with the 3-SPSU mechanism, and also couldn't be able to address the issue of passive compliance, we add another tension spring to the mechanism, and it is converted to a 4-SPSU configuration, which is correlated to a 4-SPSU type parallel mechanism to arrive at the geometric equations, and the singularity analysis is carried out to identify the feasible workspaces. So upon analysis, initial joint limits were once again set at 10 to 30 millimeters, and then the regular workspace square was identified, which led to the modification of the joint limits from 11.1 to 30 millimeters. And the tilt limits were found to be around plus or minus 5 pi by 18 radians, which is considerably better than the 3-SPSU architecture. And this configuration could be a potential candidate for addressing the issue of passive compliance and also the issue of active compliance if they are actuated. So earlier, the tilt and torsion theory was used to study the stability. So here we once again revisit the stability analysis for the Euler angles of the universal joint. So similarly, for fixed design parameters, especially for h is equal to 1, it was found that the mechanism remains unstable even under the absence of a preload. So since for the Euler angles, the mechanism has dependencies on both the tilt angles, a stable condition is only possible when the determinant of the Hessian matrix is positive and the second order derivative of the potential energy with respect to one of the tilt angles is positive. So in order to identify the optimal configuration, a simple optimization approach using genetic algorithm is carried out with the presence of preload, which tries to maximize the second order derivative of the potential energy with respect to one of the tilt angles, subject to the constraints where the determinant of Hessian is always positive, and also the objective function is positive, where the design variables are the parameters h and the spring stiffness k for a fixed value of RF is 11 millimeter. And from the results of genetic algorithm, a swarm of solutions were obtained under the presence of preload of 2 newtons along each spring for the 3-SPSU architecture and 1.5 Newton along each spring for the 4-SPSU mechanism. A common value of h 0.6 is chosen to have a compromise between both the architectures, and a k corresponding to 0.75 Newton per millimeter was chosen, which is a standard size available at the laboratory and also with the catalog. And then the stability analysis is once again re-verified for the modified design, and which led to the conclusion that a stable configuration was obtained for both the mechanisms under the presence of preload. And then a simple prototype of the 3-SPSU architecture was done, where with h is equal to 1, we can see that we have an unstable configuration under natural modes. However, in the case of h is equal to 0.6, we have a stable configuration. And then once again, the workspaces are recalculated because the value of h has been modified. And it was found that the joint limits are changed from 6.5 to 30 millimeters. And the singularity-free workspace square was identified for the 3s PSU mechanism, which was found to be around plus or minus 2 pi by 15 radians, much lesser than the earlier results. And then for the 4s PSU architecture, the joint limits are modified to 5.3 to 30 millimeters. And it was found that the singularity-free workspace square is around plus or minus pi by 4 radians, which is considerably better than the 3s PSU mechanism. So to conclude this phase, it concentrated on the proposal of tensegrity mechanism as an articulation unit. And first analysis concentrated on the theory of tilt and torsion for identifying the best posture. And the second analysis focused on the singularity analysis for the initial 3s PSU mechanism and the modified 4s PSU mechanism. And then eventually stability analysis were carried out to determine the stable configurations, which led to the conclusion that 4s PSU is an ideal candidate for addressing the issue of passive and active compliance. However, the 3s PSU can hold good only for the issue of active compliance. And these are some of the contributions at the end of this phase. So the third phase of thesis is actually split into two parts. The first part concentrates on the experiments of 3s PSU tensegrity mechanism, which tries to address the following questions like motion planning and also tilting of the mechanism to solve the inverse kinematic problem. So basically, we demonstrate the issue of active compliance where the IKP is solved for input tilt angles. So similarly, a force control algorithm is applied to have static phases at the end of a cycle. And two types of trajectory, namely linear and circular, are performed for horizontal and vertical orientations of the mechanism. And a PID control law is employed to have a closed loop feedback system. So this is the prototype, which was also demonstrated earlier. It comprises of a standard universal joint of 68 millimeters, and the corresponding design parameters are identified based on the stability analysis and also the inverse pendulum configuration. So it's basically a scaled up model when compared to the real prototype. So since we have a scaled up model, we re-verify the workspace analysis. However, the tilt limits remain the same, but the joint limits are modified from 40 to 106 millimeters. And so this is the experimental setup. The left side is a vertical setup and the right is the horizontal, which corresponds to the vertical orientations and horizontal orientations of the bio-inspired robot when it is moving inside a pipeline. So the actuation is carried out using a DC motor coupled with a planetary gear train of very high gear reduction. So similarly, the interfacing between the motors and the controllers are done using the bigger bone black microcomputer. And we apply duty cycles using PWM and GPIO. And apart from that, we use the EQUP or the encoders for transmitting the angular position information to the user. So for the trajectory planning, tilt angles are passed as input to solve the IKP. So desired positions can be calculated using the IKP and the measured positions using the gear reduction ratio, the encoder channels, and also the encoder information data. So the Cartesian velocities can be estimated as a function of the Jacobian and the particular velocities. So similarly, the 5th degree polynomial equation is employed for trajectory planning that was mentioned earlier for the bio-inspired robot. So for this linear trajectory, initially we calculate the minimum time required for performing the experiments, which is a function of the position vector and the velocity and acceleration of the motor. And the estimation of intermediate position, velocity, and accelerations are done using the polynomial equations. And eventually, the joint positions, velocities, and accelerations are computed using the IKP, the Jacobian matrices, and its time derivative. And for the circular trajectory, the calculation of minimum time is a bit different as it depends on the ratio of maximum velocity to the speed of motor. And the position vector is also a bit different as it has sinus and cosinus dependencies of the circular path. And similarly, the velocity and acceleration vectors are determined as time derivatives. And eventually, the joint position, velocities, and accelerations are computed using the same relations as shown in the linear trajectory. So we have a PID control system, which is used to calculate the motor torques which is a function of the inertia, the three constants of PID, the proportional, difference, and integral terms. And these constants are estimated as a function of the motor inertial parameters, the resistance of motors, and also dielectric constants. And so we have a closed loop feedback system where the desired position is sent to the Beaglebone black and the measured positions are sent back as feedback to the Beaglebone black. And using the proportionality constants, proportional integral difference terms, the torque is regulated and eventually sent to the user. So for the linear trajectory, two types of experiments are carried out. First one is one spring pull, and one of the spring of the mechanism is pulled and the mechanism is returned to its home post. And in case of two springs, two of the springs are pulled and it returns to the home post. So more or less, both the experiments are similar, except that it is in the opposite direction. And the choice of tilt angles are chosen exactly at the boundaries of the singularity-free workspace square of the 3S-PSU architecture. So before going into the experiments, the travel time must be determined, which are used as inputs in the control law. So 6 cycles are carried out in total, and it is around 9 seconds per cycle, which yields to 54 seconds for carrying out the one spring pull, as well as for the two springs pull experiments. And then these are the results obtained for the one spring pull. So the total time taken is around 128 seconds against 54. It was mainly due to the sleep routines induced in the control law. And these are the positions of joints for the one spring pull experiments for both the orientations, because more or less they both look similar. And the error is computed using the measured and desired positions. So once again, due to the frequency issues associated with the Beagle-Bone black, higher noises were observed. So filtering was done using, once again, the Savitsky-Golay method. And it was found that for the vertical orientation, the error ranges between -0.5 to 0.46 degrees. However, in the case of horizontal orientation, the error was around -0.46 to 0.5 degrees. So similarly, the torque values are also computed at the motor end after the filtering technique. And it was found that for the vertical orientation, the torques are around -2.2 to 3 millinewton meters. In the case of horizontal orientation, owing to the self-weight of the robot and also due to gravity effects, a slight amount of torque increase was observed, and it was around -2.4 to 3.4 newtons. And this is the experimental video of both the one spring pull and two springs pull experiment. So as you can see, one of the spring is being pulled, and then the motor and the mechanism returns to home post. And then once again, so totally 6 cycles are being carried out for the one spring pull experiments, and you can see the measured lengths that was calculated. And then we have the two springs pull. Two of the springs are being pulled, and then it returns to the home post. So similarly, we have 6 cycles for the two springs pull experiments, and the measured lengths are nothing but the IKP. So after the linear trajectory, the circular trajectory experiment is performed. So before a circular path is carried out, a linear tilt along one of the motor must be done. And then the circular path is carried out. And once again, a linear tilt to bring the mechanism back to its home post. And also during the linear trajectory experiments, when the tilt angles were chosen at the boundary, a slight movement of the base was observed. So thus a value less than the singularity boundary is chosen, which is around pi by 10 radians for the circular trajectory. So similarly, we calculate the theoretical curves. So for the linear tilts, the time is still 9 seconds. However, for the circular path, it's around 35 seconds. So the total theoretical time is around 53 seconds. However, the real-time experiments, the time taken was around 124 seconds owing to the sleep routines. And also during the circular trajectory, some intermediate one spring and two spring pull pushes could be observed. And these are the joint positions for the circular trajectory experiments for both the orientations of the mechanism. And similarly, the error is calculated by the application of numerical filters, and it is found to be around -0.04 to 0.5 degrees for vertical and -0.046 to 0.6 for the horizontal. And then we similarly estimate the torques for the vertical orientations. They are around -2.1 to 2.3 millinewton meters. However, due to the self-weight of the robot and also gravity effects, a slight increase in torque was observed for the horizontal orientations of around -2.5 to 3 millinewton meters. And this is the simulation, the experiments on the circular trajectory. So initially a linear tilt is performed along motor 1, and then a counterclockwise circular path, which is similar to the theory of tilt and torsion. Then once again a linear tilt to bring the mechanism back to its home post. So to conclude, this chapter presented the actuation strategy of the 3S-PSU mechanism under no external loading. And linear trajectories were performed one spring and two springs pull, and eventually a circular trajectory to have a correlation with the theory of tilt and torsion. And also the error between the measured and desired data were very much less. So this proved the effectiveness of the PID controller. And eventually by application of numerical filters, the motor torques were also identified, and it was found that they are well within the operating range specified in the catalog. And this is one of the contribution of this phase. The second phase of the second part of phase 3 concentrates on the optimal design of a piping inspection robot that can address the following questions, like what is the sizing for passing through a 90-degree pipe bend, and what is the sizing of leg mechanisms that could be accommodated for the robot. So this is the digital model of the existing robot with the tensegrity mechanisms. However, the problem is that if we use the existing motor units, they might pose a problem to overcome a pipe bend at 90 degrees or a junction. And also the velocity associated with the motors are pretty low and they take longer time to accomplish displacements. So thus an optimization approach is being implemented to determine the optimal sizes. Two problems are being solved, where the first one aims to determine the size of motors without the leg mechanisms. And the second one tries to determine the size of leg mechanisms for the results of the first optimization problem. So this is the optimization test bench, which is basically a 90-degree pipe bend. So it's only the issue of passive compliance, which we consider here. So this pipeline is constructed in MATLAB by discretization equations, and we have three portions of pipe, which is called the inner portion, the outer portion, and the central line radius, or CLR. And for the first optimization problems, which considers only the motor units, basically the motors are constructed as rectangular blocks using MATLAB, where the design variables are the length and width of motor on the screw unit, with the tensegrity mechanisms in between, where rotation angles are applied to overcome or pass through a 90-degree bend. The dimensions of the tensegrity mechanisms are considered fixed because the optimal dimensions were already identified in the earlier phase through the stability analysis. So the objective function for the first optimization problem is a simple mono-objective problem, which aims to determine aims to maximize the area of each modules for each displacement on CLR. And for ease of calculations, the central module is assumed to be at fully extended phase. And at each position of the robot on the CLR, collision is being verified for each module against the inner wall and the outer wall. So since we have 3 modules and 2 portions of pipe, we have 6 inequality constraints in total that will be ensured in the optimization algorithm. And then the first optimization problem is defined, which aims to maximize the objective function subject to the 6 inequality constraints and the design variables being the motor length and width parameters, and they are being set based on the catalog products of Maxon, like Hall sensor availability or maximum length of screw, and also the diameter of the screw length. And the simulation was carried out for pipeline diameter starting from 70 till 160 millimeters. And based on the results, the catalog products of Maxon were identified for each diameter, where here in the first table, green indicates optimal sizing, gray indicates undersizing, and red indicates oversizing. So based on these results, the results of 100 to 120 mm diameter was chosen, as you can see in the second table, owing to factors such as gear reduction ratio, feed force, efficiency, and also the length factors, which could be an important aspect when accommodating the slot follower leg mechanisms. So with the results of first optimization problem, the second optimization problem is carried out, which aims to identify the sizing of leg mechanisms for the first optimization problem. So the geometry of the leg mechanism is split into rectangular and triangular sections, and they are considered to be in the fully declumped phase. So since the orientation of the robot about its own axis is unknown, a projection which is similar to the second figure at the bottom is chosen to have a for easier computations and simulations. And so this is the geometry of the leg mechanism for declamped and clamped phases, and the necessary design parameters such as the length of the leg mechanism and the horizontal and vertical space factors are taken as design variables. And also we have some offsets which are mainly caused due to spaces that will be used for the assembly of leg mechanisms on the robot. So similarly, we have a mono-objective optimization problem, which aims to maximize the area of the leg mechanisms. But the central module is not taken into account because we do not have any leg masses attached to them. And then once again, we have a constraint which tries to avoid collision against the geometry of leg mechanisms with the pipeline walls. So since we have only 2 modules, we have totally 4 inequality constraints, with the central module being not taken into account. And eventually we have 2 equality constraints because the length of the leg mechanism remains the same during clamped and declamped phase. So we have a correlation between them. And then the stroke length of the leg mechanism at the declamped phase is set as 32 against 45 millimeters because we have spaces being present for assembly. And then we define the second optimization problem, which aims to maximize the objective function subject to the 4 inequality constraints and the 2 equality constraints. And we find that the length of the leg mechanisms are found to be slightly higher than the existing prototype because of the diameter range being considered for the pipeline. So this is the small simulation of the optimized robot assembly in MATLAB for 100, 110, and 120 millimeters, just to have an understanding that there exists no collision between each modules and the walls of the pipelines. So to conclude, 2 optimization problems were solved using deterministic approach in MATLAB. The first problem helped in identifying a motor unit that will be compatible for the 100 millimeter diameter pipeline. And then a slot follower leg mechanism was identified that could be potentially accommodated for 100 to 120 millimeter pipeline range. And eventually, digital model of the robot was realized in CATIA, which is not represented here, to just have an idea of how the robot displaces inside the pipeline. So to summarize, this thesis presented the design of an inspection robot for pipeline diameters less than 150 millimeters. The first phase concentrated on a rigid bio-inspired piping inspection robot, which proposed numerical models and validation, and then validation of experiments, especially contact forces. And then second phase concentrated on the design and analysis of an articulation unit in the form of a tensegrity mechanism, and also identification of ideal posture using an initial analysis that employed the theory of tilt and torsion. And then singularity and workspace analysis were carried out for the 3 SPSU and 4 SPSU mechanisms to identify the tilt angles. And eventually stability analysis was carried out. And then the phase 3 was split into two parts, where the first part concentrated on the experiments of actuation of a tensegrity 3 SPSU mechanism and solving the IKP for linear and circular trajectories, and also a PID controller for having a closed loop feedback system, and also to find the regulated motor torques. And eventually, the second part concentrated on the design of a robot assembly by optimization approach through 2 problems, and simulation and rendering of the modules were done in MATLAB and CATIA to have an idea about how the system moves. So some future works, this thesis only addressed the initial issue which was associated with movement. The rest of the issues remains open, for example, accurate positioning or even inspection activities. So this has to be validated by eventually doing the prototype and testing it on an end application such as an industrial power plant pipeline. And then the wrench feasible workspace for the tensegrity mechanisms must be studied, because this will have an idea about the forces during motion, and also experiments will be carried out using high-speed motors to have a correlation between the numerical and the experimental data. And then also experimental validation should be done on the 4 SPSU mechanism to understand its actuation strategies. And also the analysis of stability must be done for the tensegrity mechanisms, because the zero free lengths were considered to be were not taken into account. But already an analysis was already done in our latest research article by taking into account a value for the zero free length based on the spring sizing. And then the optimization approach was only done through a geometric approach. However, a simulation using software such as Adams must be done, because the dynamic parameters were not taken into account in the optimization problem. And eventually, upon validation, the prototyping will be done to test the robot inside a 90-degree pipe bend. So the 4-bar wheel mechanism was just proposed, but unfortunately it was not studied in the manuscript. So this has to be also studied in detail in the future, because this mechanism will play an important role in assisting the robot to enter and exit pipe bends smoothly, especially when it comes to the end application. So accordingly, the optimization algorithm will be modified. So alternate solutions could be considered over the existing DC motors, because, for example, a pneumatic artificial muscular system, because they are basically flexible, and they can even try to completely eliminate the use of DC motors along with tensegrity mechanisms. However, some feasibility check must be done, because these systems are sometimes not compatible with the radioactive environment, especially when tested inside nuclear power plant pipelines. And at the moment, we were using separate microcomputers for actuation of tensegrity mechanism and the bio-inspired robot. So when it comes to end application, it's not suitable, because it's not possible to operate them independently. So we should think of advanced EPOS2 CAN controller systems, which can potentially allow to operate both the mechanisms through a common central controller unit. So thank you so much for your attention.
Thank you, Swaminath, for your presentation. As I mentioned earlier, we are now giving the time to Chedli for some questions.
Thank you, Mr. President. Thank you, Swaminath, for this nice presentation. I find this work very interesting and quite complete. You have done a very good job with many validation, simulation, and theoretical development, simulation and experimental validation. I find it very good work and very interesting. And the presentation was very, very nice and clear and well illustrated.
Thank you so much.
Okay, so I will start by some question with the first phase of your work. At the beginning, what do you mean by good contact, which is not very very precise as term in terms of contact with the robot and the pipe? What do you mean by good contact?
Good contact, as in, for example, how tight the leg mechanisms try to establish a contact with the walls of the pipeline. So it's not just the leg mechanisms in general, like whatever robot we develop for the inspection robot, for the inspection of pipelines, the mechanism should be capable of having a good adhesion with the walls of the pipeline, such that they do not fall or they do not deviate from the
how do you qualify this in terms of force of contact or contact condition or mathematical condition of contact?
In this case, for example, we apply something called a threshold to ensure that the legs are tightly attached with the walls of the pipeline. So basically, it's through application of motor torques. That's one thing, and yeah, that's one thing I would say.
Okay. Do you think you can find some critical configuration of the robot inside the pipe which cannot allow a good contact? For example, if you have a bend, can you lose contact in some points, or?
Because for the bend, in fact, the experiments were not conducted because it was only carried out inside a straight pipeline profile, for which it was the threshold values are pretty good. But when it comes to reality, when it comes to the bend, it has to be re-verified if these mechanisms could really have good contact, because the profile is not going to be the same. Because when it comes to the inner portion, we have a compression because we know, like, the pipe of industrial pipelines, they are made by pipe bending stuff. So normally some materials are being stressed, and there is a compression on the inner wall and a tension on the outer wall. So these leg mechanisms might not be good, or maybe they will not accurately have a contact. So that's one of the reasons to have a 4-bar wheel mechanism on the front and the rear, which can assure that, for example, if the leg mechanisms are at the position of a bend, they are trying to have a contact, these wheel mechanisms will also lend a support to this mechanism to ensure that the robot does not move out of its position. But this can only be validated upon really doing the prototype at the end and testing it inside a pipeline, or even through some simulations.
I think contact conditions are related also in friction coefficients. So we can lose contact, some configuration due to friction, or some limit on the tangential force.
Or even the presence of deposits,
yes,
which is not even considered in this part. Yeah.
Okay, I have another remark. So it's interesting to correlate the mechanism to the parallel robot.
Yes.
But in reality, it is a 2 degrees of freedom mechanism. It's universal joint mechanism. Mm-hmm. But this work is mainly about the actuation of this joint. Do you agree with that?
Maybe I wouldn't say it's directly the universal joint, because I think it'll be more of a torsion applied to the universal joint, but I would say this mechanism is behaving in a passive mode, especially the universal. We just try to tilt the platform like we do it on a parallel mechanism. So
you have only 2 degrees of freedom, and we try to actuate or to control these degrees of freedom by some transmission with cable and control the compliance with springs.
Yeah.
Okay. So this is just a remark, general remark about the terminology used for this mechanism, and also you compare this to consider this as a tensegrity mechanism. Is it always the case? It works as a tensegrity mechanism, or you have some configuration in which we don't exactly the same operation mode as the tensegrity mechanism?
Well, I could also say that's a debate, because I cannot completely agree on this as a tensegrity mechanism, because it's actually a combination of parallel mechanism, and also maybe even it comes under the class of cable robots, I would say, to actuation of platform using cables. And tensegrity, because we have some springs in tension, and we also have some platform which might be in compression, especially when it's slightly bending or something. So that's why we call it as tensegrity too. Well, I wouldn't say it's 100% tensegrity, but it could be called tensegrity.
Okay, because I think the main issue here is to guarantee the stability of the mechanism.
Yes, exactly.
So can we have some configuration in which we have some tension, some cables, and compression and other springs?
You're saying that maybe employment of compression springs or something?
Yes.
We can have, for example, if we go for a compression spring, probably we might have stable configurations even.
Yes, because in the inverse pendulum, if we have a compression, we can stabilize the mechanism.
Because stiffness is on the opposite side, so we should have a stable configuration in that case.
Okay. Just on a general remark also, you have developed a nice dynamic model with very complicated equations and so on. Do you think is it possible to do the same work with a simulation environment like Adams software, or to evaluate the forces and the joints and so on?
Could be a bit complicated, I would say. But the idea of employing Adams is to mainly verify if the optimization algorithm is effective, because we can take into account the inertial masses and just try to make the system move. But to really feed in the equations might look complicated, but it has to be once studied or to be verified. For example, the dynamic model that was proposed for the rigid robot, it must be really checked if it could be really implemented into Adams. So yeah. But however, the masses and the other inertial parameters could be considered when it comes to, because we can assign the material, for example, on the digital model, and then try to understand if the robot is really able to displace. Yeah.
Because in dynamic model, you don't have all the contact forces between the pipe and the legs. This is I think the main thing lacking in the modeling of the robot. Okay. And then I'll move to the phase 2 of your presentation. Okay. Can you clarify something about the passive and active compliance modes? Because when you speak about active compliance, means that we control the stiffness of the mechanism.
Okay.
Here you control the motion, not the stiffness. If you want to evolve in the bend or to change the orientation of your mechanism, you need to control it as you presented in the experimental setup. You control the motion. So it's not a compliance, but I think it's a control of the motion of the mechanism.
Yes, the word compliance, which I mentioned earlier, it's not the technical compliance, but how to say, like a factor. Okay, it should have been precise, as you said, as a motion or something, because what I was about to mean is that when we have a pipe junction or a T-union, so the active compliance, what does it mean is that we need to actuate our articulation unit such that they tilt along a given path, or the path that we want to really follow inside the pipeline. So that is what I was trying to convey, and not really the stiffness of the mechanism, because it was a general problem statement. It was not connected with the tensegrity mechanism, because as I said, it was the initial problem statement. and it's not exactly the compliance of the tensegrity mechanism.
Okay, and did you determine the compliance or the stiffness of the mechanism, because this is not clear in this presentation?
I mean, we exactly
the passive, the mechanism should adapt passively to the pipe, and we cannot see the stiffness of the mechanism. If you have a very stiff mechanism, you can have some difficulties to adapt to the bending and to follow the trajectory.
I mean, in fact, those simulations are not actually taken into account, especially in optimization. We just considered like to what angle it bends. But the stiffness modeling, especially when it is coupled with the robot assembly, like what could be the behavior of the mechanism, it was not taken into account, this factor, in fact. But because, as you see, the mechanism was only analyzed under like no load condition and what will be its behavior in general. But when it comes to the real application, we need to really understand or really study, like, for example, couple the bio-inspired robot or add a loading and try to understand its behavior, especially when we have a 90-degree bend, and then understand like how it actually displaces, or like what are the forces that the mechanism could undergo. Okay, so you focused on kinematic optimization of the mechanism and not the stiffness. The stiffness was not completely done. Yes, yes. This is what I have. You showed an interesting maps of work for the workspace, singularity-free workspace, and singularity curves. This is what done by using analytical tools and numerical tools. Yes. And can we find some geometric conditions to these singularities to be more easily interpreted by the user when you design the mechanism or you use this mechanism? Can we define some geometric conditions related to the spring directions or to the geometric feature of the mechanism? One thing, maybe I would say joint limits. Like what are the limits to which the spring can go come back here? Oh, so joint limits is for the universal joint. No. You have also some limit for the lengths of the springs. Yeah, it's actually the joint limits of the springs, the prismatic springs, the 3 springs. So like to what length it can go and come back. So it was basically, initially we have a fixed design parameters. Say we started at h is equal to 1, and we have also some other design parameters like RF. So by using the inverse kinematic problem, we can try to understand what will be the length between the base and the end effector at the home post when there are no tilt angles. And then we apply some tilt angles because to start with the analysis, we cannot exactly predict like what will be the minimum length the spring can reach. So that's why we sent an initial joint limit from, for example, 10 to 30 millimeters, for which we obtained some irregular workspace. And it was, usually for a 3 SPSU, since we have 3 springs, it could be in the form of a triangle. So we reanalyzed it by identifying one of the positions of the triangle. And that's why the joint limits were remodified to 13.5 millimeters, for example, and then we identified the regular workspace zone. So this is for the workspace, but for singularity, you have the question is about singularity if you have some conditions. Conditions, I would say it's based on geometric conditions to define this singularity or to determine these singularities. Maybe I would say joint limits and also the tilt angle zone, for example, to till what value. For example, we set the tilt angles to be ranging from -pi to pi radians and -pi to pi. And based on these limits, it can try to identify using CAD like the feasible solutions, the set of polynomials that satisfies the determinant of the matrix A or the matrix B, for example. Matrix B is not taken into account because we don't have serial singularities, because it's not possible in our case, as it has to comply with the condition that the length has to be 0, which is not at all possible. So yeah, so these are the limits, I would say, the limits of the tilt angles. Okay. And my other question is about the stability of the mechanism. This stability, is it dependent on the cable pretension? Can we modify the stability condition by pretending or preloading the cables That's why, as I said, if I can move back to the slide.
Yes.
Okay. Unfortunately. Yes. So as you can see here, this algorithm mainly we consider a preloading of 2 Newton along each spring. It's like forces being applied along each spring, and under this condition, we try to analyze like if the mechanism is stable or not.
Okay. Okay. I have a question about the last simulation you showed.
MATLAB?
The MATLAB, yes, yes.
Okay, I'll go there. Yes.
So here, how you control the trajectory of the robot, how it evolves inside the pipe.
As in, like you're asking me how it actually moves?
It's like a snake, but we have no change of the length of the central joint, which should used for.
A remark that I was not able to address during the presentation. This is not the real 6-step locomotion, because it will have a 6-step locomotion, the caterpillar, like we had the front clamp.
Yes.
It was the idea to construct at the end in MATLAB. But the main thing here is to, like, we just have all the modules, okay? So we assume that both the leg mechanisms are completely declamped, and then the central module is also fully, extended. And then we have some discretized points of CLR on the central line radius. So we just displace this entire assembly at each point, just to be sure that, especially at the pipe ends, we do not have any, a collision between the walls and the modules. So that's the main idea. It's not exactly the final robot simulation. It's just to have an overview that there is no collision between the modules from the dimensions identified. So that's the main idea to represent this small video.
Okay, so this is just to verify that geometrically the robot can pass through the pipe.
Yeah, but in fact, the idea was to really do the 6-step locomotion procedure, but
okay.
some time constraints.
Do you have an idea how to plan this trajectory, for example, in order to minimize the sequences used for the traveling inside the pipe, the bending?
As in, you mean like to construct the real robot inside the pipeline and make it
If you have a real robot, how to control different motion? You have many possibilities to control it, and to have many sequences to inside the path.
Mm-hmm.
Can you have do you have an idea how to plan this trajectory for the real robot?
As I said, I mean, geometrically, it could be constructed, to have the complete locomotion sequence. I mean, it's going to be a bit time consuming, but the only problem is that we cannot, the dynamic parameters could not be taken into account. That's one thing. And maybe we won't observe any bendings, because in reality, when, for example, when the orientation is horizontal, when one leg is clamped and the other end is free, we have a small bending at the free end. So maybe that could not be constructed if we do it geometrically. So maybe that's why we have to move into other simulation softwares, maybe like Adams, where we can really define all the dynamic parameters and observe all these conditions, like when one end is clamped and there is a bending at the free end. So especially when the robot is moving through the pipe bend, we can observe that it's going to try to hit the walls of the pipeline, something like that. So maybe in MATLAB, it might be a bit, I mean, to my knowledge, might be a bit difficult to really construct the dynamic model, the simulation of the robot entirely. But geometrically, it could be done to have the visualization of the 6-step locomotion.
Okay, thank you. I have a general question.
Yes.
I think it's my two last questions. It's for the first simulation you showed, but not simulation, the experimental validation of the robot without the universal joint. Could you please show it again?
This one, the video probably.
Well, yes, please.
Mm-hmm.
Okay. So here we lift the contact. We have no contact, and when the module translates, So in this configuration, I think we cannot control completely the robot because we lose the contact, because the contact with the pipe of the first leg or the leg in contact is not sufficient to maintain, like the simulation, the straight position of the robot.
Okay.
So, do you think can we change the contact conditions to control more precisely the path of the robot?
As in, I mean, if I understand, maybe it's like when one end of the legs are clamped, the other end is free. Maybe you say that it's losing a lot of contact.
Yeah. So if you close the leg,
why? Oh,
and you lose the contact, and the module fall down, and the side of
that's one of the reason we propose that the 4-bar wheel mechanisms on the front and the rear, they ensure that there is at least 1 point contact between the robot and the walls of the pipeline. They also act as a support for the leg mechanisms. You know, at the moment, for example, also during the experiments, some slight bending was observed on the legs because it's basically the force control. So if we have the 4-bar wheel mechanisms coupled along with the robot, maybe they will also take some additional loading, and also they ensure the stability, especially when the orientation is vertical, the robot does not fall down. Because they use a spring-loaded system, and they ensure that based on the diameter, they always have a contact. So, for example, when the 2 wheels are in contact, it's just sufficient that one leg can have a contact, the robot does not fall down. But again, further investigations must be done upon prototyping.
Okay, so in this locomotion mode, we can imagine a locomotion mode without losing contact, with maintaining a contact, but we can reduce the contact forces.
Yes.
In somewhere. Okay. And my last question,
no problem.
And my last question is, so you analyzed 2 types of two solution of tensegrity mechanism.
Yes.
And we have in home position all the springs parallel. Do you think we can have some configuration or some design with the springs not necessarily parallel, or not necessary? The anchor point can be different. You analyze the different anchor position, different configuration of the anchor point of the cables.
Maybe you're saying that maybe we don't have a parallel spring combination.
Yes,
maybe it's possible when we have the dimension of the base and the end effector are not the same anymore. For example, base can be bigger and the end effector can be a bit smaller. In that case, we can have a spring which is like at an angled position, something like this. But there is one more thing. If we go for such configurations and we go to the end application, for example, the control of robot, because we do not know like which end of the because the base and the end effector are like inversible. Like one case, maybe one will be the end effector. For example, the reverse motion can be the other end. So maybe that might be a problem when it comes to the real control strategy at the end. Like when one of them is not exactly the same dimension as the other. So maybe it's better to have same architecture for the base and the end effector. And so it's also good to have parallel springs rather than having non-parallel.
Okay.
Yeah.
Okay. Thank you. Thank you very much.
Thank you, Chedli.
And thank you for inviting me to this to evaluate this work. Merci.
Thank you, Chedli. So the next reviewer is Pierre RENAUD. So the floor is yours.
Thank you, Mr. President. Thank you first to Damien for inviting me to review this work. And thank you very much, of course, Swaminath for the presentation and also the manuscript. I will not go into details about the manuscript today because we are here to discuss your work starting from the presentation. But of course, it was very pleasant to read the manuscript. And as we could see also today, the manuscript showed that you developed a really large amount of work. I would like to outline this. It's really a huge work behind all of these results. with a very large variety, I would say, of type of works, modeling aspects, kinematic analysis, design of prototypes, experimental work, including control. So it's not always that we can see a PhD presentation with all these kind of different aspects of robotics that are covered. So so it's kind of impressive work, and thanks for the presentation about that. And I think the presentation today covered pretty effectively the different aspects. So of course it's not easy because you have very different kind of works in your PhD, but you try to cover it in a quite clear way all the different aspects. So I will have a few questions, maybe to clarify some points related to the context first, because of course we have two aspects. We have the design of a tensegrity mechanism, but not by itself, but included in a general system for this inspection application, inspection of pipelines. So I will start first by a few questions related to this. Maybe first just to outline the context and the intended use. So what kind of load, what kind of embedded system will be integrated in the robots? And in other words, is that workload possibly of impact in the design, or can we neglect everything needed for the inspection itself?
As in, to clarify, you're saying that any specific loading on the entire robot, or like which is concentrated on the end application, such as an inspection or something, or?
Just to understand if by inspection we only talk about, I don't know, visual inspection, and we can consider that it's just lightweight camera and we can get rid of that and there is no constraint associated to that. Mm-hmm. Or it could be in some context inspection when the non-destructive testing with more a larger weight, potentially interaction forces between the robot and the pipeline. So yes. What's the requirement according to you about that?
So generally, Pierre, we have, as I outlined in the beginning, generally we have 4 issues that I stated. The first one is like how the robot moves inside a pipeline. That is the main objective. And followed by that, like how we position this, like on the desired zone. For example, we have a crack on a given position and we have to be sure that the robot is on the desired zone or not. And then next comes the final, the real task of the robot, like if it has to perform a visual inspection, like using a camera, for example, or if not an intervention, like if it has to do a drilling or like, seal a point of the pipeline, but like by, having all the devices accommodated on it. And while doing so, like what will be the forces that will be like transmitted on the entire robot system, if it could really withstand all these forces or not. This thesis, in fact, mainly tried to address only the first issue, which was associated at the movement. So the main thing is like how we accomplish the movement inside pipeline. And then the other applications were like, as a part of future perspective, upon validation of the entire prototype, some improvements could be done to really identify like what will be the final task of this robot. So if it will be like only limited to visual inspection, or if it will be like just concentrating on tasks like, drilling or welding on the desired zone. But, accordingly, the architectures must be re-verified. So also, you see, one more thing which I addressed in this thesis was it's for diameters less than 150 millimeters. So you could imagine if we go for tasks like welding or drilling, maybe it's ruled out, it's very difficult. But maybe this robot might be limited to visual inspection, such as, especially in nuclear pipelines, we have some small diameter pipes to carry the feed water or something like that. So in such zones, if we need a frequent inspection, maybe this robot can take care of only the inspection task and not really do some activities like sealing or something. So for that, if we really have to do some intervention activities, we should really think about, modifying the architecture according to the end application.
Okay. Thanks. Still about the context, and the umbilical cord that will be placed between the robot and the outside. So according to you, what would be the typical length of this cord? Because I had this question in my review about the impact on the behavior, because if when you start to insert a wire into some kind of network of tubes, if you did this, for instance, when you do electricity at home, you know that friction is just becoming huge, and it's very painful to try to put tension on the wire. So we may expect that the tension actions on the device may become significant, and so. But it's also related to the length of guidance and how far is the robot from the remote control. So do you have numbers, or what's your opinion about that?
To be honest, I don't have any specific number, like how long it would go. But really, when it comes to the end application, cable management is another issue that has to be taken into account, because there are chances that we never have a regular pipeline profile, that's for sure. For definite, we have some bends like 90 or junction or whatever. So especially in feed water pipelines, one case today I would say, we normally have zigzag type orientations in some cases. In that case, managing cables would be a hectic problem. As you said, frictional effects going to be a very big workload, because and at the end it will be imposing more tasks on the humans to concentrate on the robot architecture. So maybe an alternative could be thought of making it even more autonomous, like to have at least some I don't know, like having some power source to be also incorporated that could be actuated from a distance, because the idea is to also at the end application to have less number of cables and not more. And yeah, because if you have more cables, of course it's going to pose a lot of problems. So as I said, to be honest, I don't have exact figure like how long. Maybe I would say for the moment, for sure, as I said in the experiments, it works for 2.5 meters, which is very, very small, and it's not acceptable also when it comes to the end application. But normally, for example, for 100 meters, we should think of a very good solution. Maybe try to mount, the power devices or an external power source directly and control it autonomously from outside. Yeah.
Okay, thanks. Chedli asked about contact problems and the nature of contact. So maybe to come back also to that point, but once again, more about how you consider the field of applications. In your manuscript, you mentioned the possible presence of dust, of deposits that will impact the inner surface of the tubes. So you have this remark, and also actually at the end of the manuscript, you have a remark in the conclusion about the possible use of technologies in the nuclear context, where you say that you have something like pneumatic cannot hold good in that context. So that remark, is it related to the presence of dust and you don't want to move deposits because of the pneumatic technology, or is it disconnected? And then why do you want to reject pneumatic technologies for this kind of nuclear applications?
Okay, so Pierre, we started with a case study robot, which was already proposed at LS2N. So the idea was to continue with the same technology and try to improvise the design for the end application. So it's not like exactly we started with from scratch a design of an inspection robot. That's one point to be to comment. And the other thing is upon literature, there are chances that when it comes to application inside nuclear power pipelines, pneumatic artificial muscles, that's what I mentioned. So we should be very careful in choosing the material, because sometimes they are not they're not compatible with the radioactive materials. Maybe they decompose. That's one thing. And that's not the main idea to go for pneumatic systems. The other thing is, if we go for a pneumatic system, we can potentially completely eliminate the DC motor system or the tensegrity mechanisms and just have a pneumatic systems, because they can also try to adapt its structure and also have contacts. But no, it's completely modifying the entire design. So it's just an alternative. But it's possible to have a caterpillar locomotion. So accordingly, we adjust the, the modules and have the elongation or compression modules. And also, these bellows are, commonly found in colonoscopy applications, for surgeries and stuff. So we can try to have, based on those literature, we can have, a design of an inspection robot that can do a similar task that it does for a colonoscopy purpose.
Okay. So, so your remark was at least related to the possible issues with material behavior in
Yes.
because of the exposition to radiations, ionizing radiations. Okay, I better understand. Thanks. Now about the selection of solutions in your work. I had this remark about the scoring you've been using as we always do as engineers to try to compare solutions. And for the articulation unit, the bad news is that universal join is the best solution with your table. So beyond that, because of course I can understand that you don't want to develop a simple universal join in your work, and tensegrity mechanism is much more exciting. But behind that, actually, maybe one question is about the criteria you've been using in your table. When we see that table, actually, maybe that table is built also in a way that it doesn't really favor possible continuous solutions, because we can expect that when you want to bend in the pipes, when you want to follow complex paths, it may be difficult with architectures based on a discrete number of components, because it's always difficult to follow more precisely a complex kinematic path. So if you had to revise that table, what would you say? It's more the scoring that would need to be changed, or after also all the work you've been doing, maybe we would need, considering also the results you have, we would need to add other selection criteria. What would you say about that?
Okay, so Pierre, I will say I will not remove the table, but you can stop me from doing that. The thing is, if I analyze the literature carefully, so usually universal joints is one solution that's pretty much found in most of the existing inspection robots. They are actuated and they can bend up to some angle and really help the robot to overcome such systems. And apart from that, the main idea is to have, as I said, tensegrity mechanism is something different, to have something different from the existing literature rather than going for a simple universal joint. And to be precise, I also mentioned at the end of synthesis that the idea is to not exactly go with the solution that has the best score, but maybe we must exploit a system or arrive at a system that can exploit the advantages of one or more components. So that's why, if you see carefully, we arrive at a tensegrity mechanism that has a universal joint and also some springs. So at the end, we call it as a tensegrity mechanism. So I would say it's a combination. So we exploit the passiveness of the universal joint, and we also exploit the passiveness of the spring. And at the end, we exploit the advantages of a tensegrity mechanism, like actuation strategies, like how it can pass through a given environment. So that's the main idea of this table. So just having the advantages of the system, and if you go one by one, as you said, you're right. Like universal joint is always the best candidate, especially for inspection robots, and they're also lightweight, to be honest. And so this is the main idea, like just have the advantages of all these systems. And also going back to the locomotion techniques once again, as I also proposed to the mechanical and bio-inspired systems. If you look into that, I also said maybe wheel is like one of the best candidates, and maybe I don't know, like worm type is also an ideal candidate. So the idea is to exploit all of these things together. One good thing is, like, you have a design with the worm locomotion, and one thing which was not considered in the manuscript is the incorporation of the four-bar wheel mechanism. As I said, the wheel mechanism will also be coming into play at the end with the entire robot. So we thus exploit the advantages of the wheel as well as the leg systems, such that we address all the required criteria that was mentioned in the table. So that's the main idea of the synthesis table, in fact.
Okay, all right, thanks.
Yeah.
My comment was not about suppressing the table, and
Okay.
of course, I mean, it was just more a minor point to outline this, and we also know that we never just simply select the best solution in terms of score. Behind that, you have different reasons that
Yeah.
you clarified here. So of course, when we do design, we just don't just stick to the maximum note and get rid of all the comments behind.
Yeah.
Maybe one question or one comment about the general architecture. So in the end, and you discussed this already, in terms of load on the contact points, and load actually more about on the tensegrity mechanism. When you will want to turn, if you have two possible paths and you need to select one,
yes.
So you will actively control the system to try to turn the system and go in the right direction.
Yes.
So that means you need to be able probably to develop quite significant forces or torques in order to turn the tip of the robot to do that, because the part of the system you will move will have a significant weight. And actually also during locomotion, as you discussed already with Chedli, you have some phases where the load on the tensegrity mechanism will be significant because of the weight and the motion pattern. You made a comparison with the medical field, and of course you can there is a kind of natural comparison you can make. In the medical field, there is often a technology which is to use a so-called guide wire when you want to navigate in arteries. So you actually separate the main object that you want to move from a simple wire, a very lightweight wire that you will use sometimes just in a passive way with a hook at the end in order to adjust the path and select the correct branch of path you want to follow. Did you consider a solution where you would have some kind of internal system inside your general robot? So a kind of wire which is lightweight that you could control, and for this there is almost no load applied on it, so it's a very lightweight system. Just to go in the right direction, then you fix it to the pipe. You have contact between the end of the wire and the tube after the branch, and then the robot will passively, naturally follow this path, so you don't have to exert large forces in order to reach the right location. I'm not sure I'm clear about the description, but to try to decompose between the robot and the exploration subsystem.
Yeah, I got the point. Like it's basically, guiding the robot beforehand. Like this has to be the path it has to follow, or maybe just to clarify, the wire which you mentioned, maybe it's something which is autonomous, or we define controls for this thing to follow the given path or something. Like, do you?
Well, in your system, you could have a control of the orientation of the wire that would come out from the robot. And in that case, the control would be easy because it would be a very lightweight system. So you move it in free space, then you anchor it on a remote location where you want to go, and then the robot will have to follow just simply the guide wire that you placed along the right path.
Oh, I mean, exactly. We did not investigate something like this, but we had an idea of maybe a year ago, like even with Ramki, we had a discussion, like, probably have the application of machine learning techniques. Like, we have a camera and try to read the pipe profiles, but this will be like additional incorporation of the system onto the robot. So based on the profile, we can understand and, remotely control the system from a central unit, to choose the path. So that's one, yeah. But in terms of load carrying capacity, that was not taken into account, as you said, because if it is going to be a T-union, for example, maybe the robot can easily go if it's a straight path, but if it has to go up, a lot of forces have to be applied, but those factors were in fact not taken into account. So maybe, as you said, we should think of a solution like a wire or something which can go and, create a guide for the system and help it move along the path. So this is maybe a consideration we can take into account.
Okay. Now, just one question about the design, about the selection of the tensegrity mechanism. So there are so many definitions of tensegrities and tensegrity mechanisms that actually that could be a whole discussion. Is it really a tensegrity mechanism and so on? But anyway, initially I thought, and I think I put that in my report, I thought you would assemble the cables and the spring not in parallel, but in to have them serially connected. So you would pull on the springs in order to adjust the orientation. And then this way it would be kind of easy to put, to add an internal constraint in the system in order to modify the stiffness. So why this arrangement of having cables and springs in parallel and not in a serial connection?
So serial connection as in like, 3 springs in line or something like that?
So let's say three kinematic chains between the base and the end effector. And each kinematic chain is the cable mounted on the spring, and the spring is mounted on the end effector.
Okay. I did not analyze in that way.
Okay, but then to put it differently, did you investigate different ways to add this compliance with the springs in terms of architecture, or was that architecture kind of natural to you, or how did it happen?
One thing is, pretty natural it was. And the thing is, we tried to analyze various postures. For example, it's not just the case of, the inverse pendulum. Maybe we can also have other configurations like, from the base to the universal joint. However, the distance from the universal joint to the end effector is not exactly the same, but some other value, maybe like 0.5 times the previous length. Some analysis were done, but at the end result, what we found was the workspaces were comparatively better for this configuration. So, and we thought the tilt limits are sufficient, and also geometrically, we were able to understand the optimization algorithm, especially in the final chapter. So that's one of the reasons we stuck with this mechanism. But at the end, all validations can only be done if we have the real prototype and understand the consequences, especially when we have loading on the mechanism, or even when you assemble the robot together. So that was actually the main idea, to have a prototype made out of the entire assembly made out of rapid prototyping. But owing to some lockdown constraints, we were not able to really have the entire robot assembly. Or probably we could have had an idea like how it might be, and based on that, we could have went for some modifications of the tensegrity mechanism if necessary.
Okay, my last question to leave time to other members of the committee. If you can come back to the conclusion and perspectives, especially just the slide on the perspectives.
Yes, perspectives or the conclusions?
Yeah, about the future works. Yes. So that's a kind of significant list. We have many different elements from very practical technological issues, like I want to change the controller, yes, to more fundamental issues. What would be for you the most interesting aspect, the most promising aspect in terms of research that you would like to outline and you would like to push more if you had more time in that list?
Well, I would say like 2 things. Like one was to mainly, validate the optimization algorithm that was developed, to really validate the algorithm through dynamic simulations, and then eventually to have a complete prototype. So the idea is like the entire new design of the robot. It's like like an elephant trunk, as I mentioned in the manuscript. So just to have a correlation to a bio-inspired system under passive modes. So that was the main idea. And also based on that, we thought of, arriving at some actuation strategies on completely controlling the entire robot as a whole. So that was the main thing that was supposed to be carried out at the end. And yeah, that's one main thing. And also the tensegrity mechanisms, like further analysis must also be done. And one more thing which I want to add up here is like, the stability analysis was also, in our latest research works, we considered the factor of free length also, just to be sure, like what are its influences on the mechanism, because the analysis which I presented was like, we considered them as 0. So, and pretty much there was not significant difference, but maybe the value that was chosen was significantly smaller, but maybe due to the presence of free length, we can have even more higher value, even more better workspaces. So that's one thing I would also want to incorporate, at the end to have a, proper design.
Okay.
Yeah.
Thanks a lot for your answers and for the discussion.
Thank you, Pierre.
Thank you, Pierre. So now we will hear from Ramki. Hello, Ramki. Do you hear from me?
Hello. Yeah. Thank you, President. Thank you.
Thank you.
I would like to thank Dr. Damien for this opportunity to review and evaluate his thesis. Thank you so much, Damien. And hello, Swami.
Thank you, Ramki.
I hope you are doing well. Hi.
Yeah.
It was a very nice presentation and well presented and very informative. And yeah, you have comprehensively covered both theoretical as well as experimental validations for your thesis, and it's a quite lengthy work what you have done, like phase 1, phase 2, and phase 3. So very informative as well. So there are few clarifications and some suggestions I would like to present here.
Sure.
So the first thing is like, did you explore continuum robot mechanisms where you have used conventional actuators? Did you attempt of trying SMA or elastomus or the continuum mechanisms in specific? I'm not concerned about the actuators, but continuum mechanisms. Because you have mentioned biologically inspired, right? So as you said, elephant trunk kind of mechanism would be more appropriate, which is close to continuum robots. Any scope for it? This is just a general context of this presentation.
Like as in, you're trying to say, like, for example, shape memory alloys, like, or maybe some bellows or actuators sort of things, right? That's what, yeah, maybe that's one of the suggestions I added at the end. Maybe we can go for artificial muscular systems. I mean, it can potentially replace the entire motor assembly with the tensegrity mechanisms, reducing a lot of work as well. That's one thing which was proposed as an alternative. But to be frank, I mean, we did not really investigate like what are the things like SMA or something that could be really incorporated as cool.
Okay. Your mechanism, what you have proposed, would like to know whether it can work on different diameter pipelines, whether it has got the reconfigurability options.
The tensegrity mechanism or the entire robot assembly?
Any mechanism, like the phase 1, phase 2, phase 3 mechanisms.
No, at the end, it's like, Ramki, the main idea as I outlined, it's to have an inspection robot less than 150 millimeters. So the first rigid model that was proposed, if we have a perfectly straight pipe, it can operate between, diameters from 40 to 94 millimeters. Okay. But the idea is to have a flexible system, to mainly cover bends and junctions. So, but based on the actuators and the leg mechanisms used, we cannot really have, a broader diameter range. So that's why through optimization approach, we re-verified everything and we were able to, limit the diameter range. If you see at the end, we arrive at the robot, which is just limited to 100 to 120 millimeters. And so maybe if you imagine, if I want to work in a 90 millimeter pipeline, it might not be suitable. So we have a robot which is less than 150 millimeters, a flexible system, but only suited for 100 to 120. So that's the global conclusion.
Okay.
Yeah.
So since your mechanism would be used for defect identification as well as inspection in the given pipeline, we cannot expect the pipeline to be sometimes, this is the real challenge, there may be some defects, physical defects in the pipeline. Due to that, it may be eccentric also sometimes, or sometimes it will not be exactly, concentric. that is because of the mechanical defects on the pipeline. So such cases, I'm just interested to know like how this mechanism would work. Like maybe that could be addressed in the future. So coming to your presentations, like would like to know what are the assumptions you have made for this study, like say simulation as well as the experiments. So one was the horizontal pipeline considerations. So any other assumptions have been made?
You're saying for the, for example, the first phase where I represented an experiment inside a horizontal pipeline, or it's like
all simulations. All simulations. I mean.
Okay. Concerning the simulation of the rigid robot, which was presented earlier, it was tested for vertical as well as horizontal orientation, but only straight profiles. That's one thing. And then moving on forward, the next simulations or experiments was on the tensegrity mechanism. And it was also horizontal and orientation, just because to have, it will be actually, the idea is to incorporate with the bio-inspired robot. So that's why it was also tested in, horizontal and vertical orientations. And also the influences of motor torques, especially when we have an horizontal orientation, was interpreted. And lastly, the optimization, it really did not take into account, the dynamic parameters. So it was purely a geometric approach, and it was, made to move along a straight pipe profile and then a 90 bed and a vertical pipe profile. So these are the assumptions or things that were considered as.
So your stability analysis for a static condition is one of the assumptions, because dynamic stability was not addressed, like where static analysis. Static stability, I mean.
Stability analysis mainly done for the tensegrity mechanism was done only in the static modes. No, it was not in the dynamic.
Okay.
Yeah.
Then in your slide number 9, you have mentioned multi-objective optimization. So
Yes.
did you find any trade-off situations over there?
Actually, I did forgot to mention one point. This was also one of the things that was carried out initially when the robot model was proposed. It was done earlier. It was an earlier work proposed by another candidate. So this multi-objective optimization approach took into account the objectives being to minimize the inverse kinematic problem and maximize the force transmission factor. So that's why we stuck with these dimensions for the initial design. But the optimization approach presented in this manuscript, which is in the second optimization problem, once again we recalculate the dimensions of the leg mechanism, but through a single objective problem, but not using the kinematic equations, but the geometric equations, to simplify what will be the dimensions of the leg for the 100 to 120 mm pipelines. Yeah.
Okay, and in slide number 20. So you had shown an experimental validation result, wherein did you do any error analysis? Because it's an experimental data. So
Yes.
generally multiple times, if you do the experiments, you would get different values. So did you do any error analysis to represent, like say plus or minus, what was the percentage of error you could find there?
For this experiments, I did not do, because I mean, it was like, the experiments were carried out multiple times, but there was some slight variation, as you mentioned. It's good that you said, but they were not so significant, I would say. But
okay,
but for this one, it was not.
So almost less than 5%, I guess.
Yeah, but
it should be less than 5%.
Should be. I remotely remember the values, so because it was carried out around 2 years back, so.
Okay. No problem. So just want to know, you had mentioned you have used fifth degree polynomial equations in slide number 48, as well as in phase 1 somewhere you have mentioned that you have used fifth degree. So why did you fix the fifth degree, as in what basis it was fixed as fifth degree?
So, I mean, it's just like polynomial equations, and to have a smoother trajectory.
So like what all the complexities or the non-linearities you have considered over there to make it a fifth degree, because the non-linearity has up to a degree of 5. So on what basis?
We can go for a simpler interpolation equation, like just calculate difference between initial and final position, and just take the time derivatives. That might look simpler, but the problem is the accuracy or the error data that might arise by using simpler equations. And during the experiments, or during, for example, the experiments on the tensegrity mechanism, or even in this motion profile, I mean, the only thing is it takes some time to, to arrive at the planning or the trajectory. But the main thing is the accuracy that you get at the end. So going for a simple profile might, it's not a good suggestion. Maybe it's less time consuming, but the accuracy might not be good. So that was the main thing we stuck with this profile. And since this dynamic model was already proposed earlier, so we just continued with this thing. And however, for the experiments, conventionally for the for PID control, we normally use the 5th degree polynomial equation. So we just stuck with that same procedure, and also to have a good correlation between the measured and the desired data, and also to reduce the errors. It's better to go with the 5th degree polynomial equation.
Okay. In slide number 20 and 21, you had mentioned the simulation results and the experiments. Okay, sure. So here. Why such no major difference? Like, is it because of the non-linearity present there?
You're saying the experiments in slide 20?
Yeah.
No, actually, the polynomial equation was a numerical model, but in the case of the experiments on the rigid bio-inspired robot, here we do not have the 5th degree polynomial equation. This was just a normal profile, like the one which I said earlier, because we just considered that way. And that's why if you see, for example, at the start of each phase, we observe a sudden increase in force, and then we have a force which is reduced, and then once again it increases. It's mainly because we used a constant velocity profile in the control law. So that's like suddenly when you have a constant, like for example, 3000 RPM, when it is suddenly applied, you have a sudden starting torque. So that's why we observe a sudden peak at the beginning of the experiments. But this was not the case for the tensegrity mechanism. It was much controlled using the PID and stuff. So,
okay. So your PID controller, whether you have tuned your constants, the PID constants?
Yes. Based on the inertial parameters of the motor specification and stuff, it was tuned and arrived at the value called omega.
Okay. So this is my last question. So I was quite interesting to know, like, how did you bring about in the video the circular trajectory what you have shown? So I could see the linear trajectory.
Like, do you want to
the circular
open the video? Like, do you want me to open?
Yeah.
Okay.
The circular trajectory.
Yes. I'm sorry. This is the linear. Okay, so initially we have a linear tilt, and then we apply the circular path.
Okay, so how did you bring this trajectory? Like, it's quite interesting to know. It's very nice.
It's just sinusoidal, sinus and cosinus terms. Equation was just basically the equation of a circle, but bit of a complex form, which appears something like this.
So you need an interpolation, circular interpolation you have done on the kinematic.
Because there was another robot in our laboratory, which also did a circular trajectory path. But the paths were the geometric equations were quite similar, but I had to remodify some things to arrive at this exact circular path. So initially I did some trial and error using MATLAB to arrive exactly at the profile of the circle, and then I just transferred it to the control law in C to trace it.
So like if you do real-time robot motion measurements, we will know the exact circular trajectory which is being developed over there, like using an non-contact measurement.
Okay. No, but this was arrived upon literature of the existing work that was done on another robot, and then I just did some manual tracing in MATLAB, and then, as I said, I transferred it.
Okay. Yeah. Okay. Thank you so much, Swami. Thank you.
Thank you, Ramki.
Thank you, Ramki. So the next speaker is Margot.
Yes, thank you, Mr. President. Thank you, Damien. Thank you, Swaminath, for this nice presentation. It was pretty dense. You did a lot of works in this PhD thesis. I would try to be quite fast, so I will ask just two questions. So yeah, the presentation was pretty clear.
Thank you.
I was a bit sad that you didn't add more drawings to facilitate the understanding, perhaps, of some models and whatever. But still, I have 2 questions. So the first one concerns the static model. Mm-hmm. So you use a very simple static model. So basically, you consider that the 3 contact force at the leg were equal, and so you did this momentum equilibrium at the center of gravity, which is a very nice way to begin to estimate the clamping force, and the results are pretty surprising. I was pretty surprised that for the horizontal pipe, you have something about 100 Newton, while you have just 10 Newton on the vertical pipe. But anyway, okay. Yeah. So this difference is pretty surprising. That means that the momentum creates a very important actuator force. You need a very important actuator force to compensate from the momentum. But looking at the experimental video, so we see that the robot is kind of tilting, and you explain this phenomenon by some flexibility of the robot joints. I'm not sure that this tilt of the robot originated from flexibility. I'm more expecting some slippage or rolling at the contact point. And so my question is, could you consider this kind of slippage in your static model and anticipate this phenomenon?
So Margot, the thing is, you're right. When you have the clamping in one of the set, the other end actually bends a lot. It's mainly due to the self weight of the robot. And so that's why in the static model, what we considered was like, this end, the one end is fixed, the other end is free. And because of the gravity effects, we just consider the self weight is imposing a moment on the clamped end. So that was the main assumption taken into the static model. Not exactly a slippage, I would say, but also the coefficient of friction was taken into account. Not exactly for the experiments. To be honest, for the static model, the coefficient of friction was between a bronze material of the leg and a steel wall of pipeline. But the experiment was actually carried out inside a PVC test tube. So maybe there was a lot of slippage. That's one thing. So maybe we should really try it inside a steel pipe and see. I mean, the problem is we won't have any visualization. Unfortunately, we don't have any cameras being mounted or to really understand what would be the bending. So that's the main reason we had to go for an experiment inside a PVC test tube instead of a steel pipe. And to come back to your point, surprising results, as you said, the main thing is the equations which we arrived for the radial and longitudinal forces for the clamping model. The longitudinal forces had a dependencies on the cosine of the pipeline orientation, but the radial forces are purely dependent on the weight of the robot. So that's why when we moved to the vertical orientation, there were like no moments induced on the free end. So that's the reason we just have the influences of the radial forces. And that's one of the reasons you see, as you observe, we have a constant profile for the vertical because the longitudinal are totally zero. But since we can have multiple orientations of the robot about its own axis, we have a kind of sinusoidal or cosinus waveform for the horizontal orientation. Yeah. Okay. Yeah. Thank you. So that leads me to like 2 questions about design. So I read in your manuscript that the legs of the robot are in bronze, so which will lead to a low friction coefficient between the pipe and the legs. So can you justify this choice, and could you choose other materials which will increase the friction and so increase the way your robot can stay on the pipe, on the wall? So in general, when it comes to the end application, we for sure have metallic pipelines, which can be steel or something else or some alloys. The main idea of choosing bronze is that it's a self-lubricating material. So maybe we can try to avoid some, the lubrication stuff. So that's one of the choice being made to go for bronze. And also we can even consider going for, some flexible materials, but we should also take into account like what are the forces that the legs can undergo. Maybe there were also some deformations observed when we were doing the experiments. So to have a compromise of all this, that's one of the reasons we stuck with this choice actually.
Okay. But you could have a different material for the leg tip and the path of your transmission.
Okay.
But anyway, and so my second design question would be about your articulation. So you showed that you have a very interesting articulation with 3 springs and the universal joints.
Mm-hmm.
And so you show that you can pretty precisely control the orientation of this articulation, so which is very interesting if you want to pass through T junction in your pipe. So if you want to control this mechanism, you need at least 3 motors per articulation. So for your robot, you need at least 6 motors. You discussed about the way you will integrate these motors inside the whole robot, and what will be the impact of the weight of the robot on the contact force and the slippage of your robot?
So as in when I integrate completely the tensegrity mechanism and all those cables, like, what will be the influences on, for example, the static model which I presented, maybe what will be the real-time influence when I have all these things together? That's what you're trying to ask, or?
Yeah, and particularly if you want to actively control the articulation, so you need 3 motors which are pretty heavy and that you need to integrate inside the body of your robot. It's more like, what will you do to integrate this actuation part of the articulation inside your robot?
The problem is we will not be actually integrating the motors exactly along with the mechanism. That's one thing. So it will be like, again, going back to the issue of cable management. The idea is to have, again, 3 or 6 set of cables that is going to actuate the tensegrity mechanisms as well. So we are going to have a bunch of cables like going to a central station, and also the cables of the motors. And that's like one pain point of having the entire design at the end. So it's not like, really incorporate or integrate the motors of the tensegrity mechanism onto the assembly. And the next thing is the experiments that were carried out on the tensegrity mechanism. They used high velocity motors. Very low velocity. It was at very low velocity because we had a very high gear reduction. That's mainly because of the motor that was available at that moment with Maxon. We couldn't go for with the very low reduction. And maybe in the reality that will not be the exact motors that we'll be using, because it takes a lot of time to really tilt the mechanism. So we should think of an alternate high-speed motors. That's one thing. So it will reduce the weight for sure of the motor, of at least the tensegrity mechanisms. And as I said, cable management will pose a lot of problem because it's not going to be accommodated on the robot but from a central station. But we should actually think about having some autonomous system that can control the mechanisms from a distance or something. So yeah. Okay.
Okay, just like one last question.
Yeah, sure.
So you were talking about a force control approach. From what I understand, it's more like, so you are controlling the voltage you are applying to your motor to clamp or declamp. So it's more like a velocity control where you look at the threshold, and when you reach a certain current threshold, you just clamp your mechanism. Could you imagine a controller like in the future which integrates wall force control at the leg tip? So could you be able to control while controlling the motor torque to control the force you're applying to the wall, and then actively control the slippage of the leg on the wall?
The idea is like to not go for a force control algorithm, in fact, because we were thinking of going for a position control, which was also like presented briefly in the manuscript. Like we have 2 types of algorithm, like force and position. So the force control basically like through the current we regulate the torque and to have the applied forces on the walls of the pipeline or actuation of the tensegrity mechanism. But the idea is like maybe with the position control, what we can do is we can really try to, based on the the encoder data of the motors used for the leg actuators, we can try to create a link between the travel distance or the displacement between the leg mechanisms till the distance to which it reaches the walls of the pipeline. Because the problem is that with the force control algorithm, we cannot predict what is the diameter of the pipeline. So that's one of the reasons, like we have to put some threshold limits. And this threshold limit presented was highly limited to only one diameter range. For example, if we go for other diameters, it's not going to hold good. Maybe it's even reduced or even it's higher, we never know. So in that case, if we have a position control algorithm, so maybe we can try to create a relation between, the leg travel distance, and based on the initial contact, it can understand, okay, I'm reaching this position, and we can cut off the velocity or, stop the current flow to the motor and have the static phase. So that's the main idea. And that also tries to, eliminate the need for using thresholds in the entire system. But in the case of the tensegrity mechanism, it's more of application of torque. And main thing is, like, since we used motor with very high gear reduction, we stuck with using the force control algorithm. Yeah.
Okay. Thank you very much for your answer.
Yeah, you're welcome.
Thank you, Margot. So we will ask to Olivier now.
Thank you, Mr. President, and I would like also to thank you for the presentation, and that presentation was clear for me, and I agree with all questions and remarks made before. Yeah, I think you've done a great job. That was difficult between something that looks like a theoretical aspect that you need in a thesis, some experiments, and also works linked to a real project, to an engineer, let's say an engineering project with real constraints. So you had to deal with all these things, and yeah, I have maybe a little criticism on that. Is that you choose to in your presentation to split the problem in several parts and deal with all these parts in a separate way. And I think everything is correlated. That's one of the criticism. But you can only know that at the end. So it's very easy to come at the end and say, yeah, you don't have taken into account the relations between the mass of the central module that you can estimate before with actuators or things like that, and the mass of all the features of or the specifications of the clamping system. And also, something I found strange in your work is that it seems that you by theory you find the good solution, and in the experiment you have the bad solution. Just for instance, I think you have the 3-spring system that you tested, and during your theoretical exploration, you found that a 4-spring system was better. So this, I think, this can also in fact, you can avoid the 3-spring systems because, yeah, you cannot generate something square with 3 points. So we have this experience in parallel cable-driven robots. The first one we built was like a platform with 3 pillars. And yeah, at the end, the workspace was really, really small. So if you want to have a square at the end, start from a square. That's so. Why? I think there are constraints, experimental constraints that let you do things different than the optimal solution in your thesis. That's only an example. Things like this can be found at other places.
If I can add a point,
Yeah.
Yeah. So the thing is, as I said, at the end of phase 2, the 3-SPSU architecture was good for active compliance, but 4-SPSU was ideal for active and passive compliance. So the reason why we did the experiment on the tensegrity mechanism is to understand how we do the actuation strategies. And there were some limitations of why we went for the 3-SPSU. One thing is we used a microcomputer, the BeagleBone Black, which was actually used for the bio-inspired robot, you know, to reduce the time for writing the algorithm, and also, you know, didn't require a lot of time. And the main problem is that this controller in fact supports only 3 encoders. So unfortunately, we couldn't have a 4th encoder to have the 4-SPSU architecture. We actually did the prototype of the 4-SPSU mechanism, even the test platform. So that's one of the reasons we limited to having a demonstration of the 3-SPSU mechanism. And the main idea is to actually really validate the 4-SPSU, because in reality, that is going to be the main architecture that will be going inside the robot. So one thing is like there were also like other experiments in our laboratory which employed, you know, another microcomputer from BeagleBone, which is the blue. So this computer actually supports 4 encoders, but owing to the limited time, we couldn't, you know, go from the one microcomputer to the another. So that's one of the reasons we limited to this strategy.
Yeah. Okay, so that is not that's a kind of good reason. So maybe just mention, because the reader finds strange that you state that it's a good solution and you do something else, and or maybe you can explore and add an extension board to the BeagleBone or build something to read a 4th encoder. You can buy already this kind of system for PI or Arduino that already exists. So
Okay.
maybe that could have been different, and that's the same kind of remark states for also you say that you generate a phase order polynomial for the past generation, and then yeah, in your test you only use constant velocity steps. That's strange. And that leads to bad plots.
Okay.
And why also you in this experiment you don't try to put the real law that you say that's the good one?
The real load, did you mention?
Let's say it was on your slide 20, if I remember.
No, I mean, I couldn't exactly get to the point, because just to clarify, you're talking about the experiments on the robot or the tensegrity mechanism?
On the chapter 2 or 3 at the beginning, when you test the system that is deployable system.
Okay.
Yeah. So if you can put slide 20, I think you.
Slide 20?
Yeah.
Okay.
Just okay. So here,
yeah.
That's related to the here. You see that the peaks are. You justify the presence of the peaks, saying that you use constant speed for your experiments.
Yes.
That it was so complicated, so complex to use polynomials and to avoid this kind of bad plot, instead having the good one without the peaks.
You know, I mean, we could have actually went for, you know, other profiles like trapezoidal or bang bang. You know, maybe we could have got a better correlation.
Yeah.
But the main thing is the operating forces would be similar, I'm pretty sure, because it's only the peaks at the beginning that created this issue. But if you see after the drops, the operating forces would be pretty.
I just say that the plots are not as expected and stated before, just linked to constraints of the experiment, and that could be better if you avoid this and have the good plot. Of course, when you are in the step, it's good, but the transition can be, the bad transition can be avoided. Okay. Yeah, I had some questions that you already answered. If I understand well, your answers to Margot. Yeah, the central, no, not the central, the tensegrity module, let's call it like this. You will use in the real robot 2 of them.
Yes.
Yeah. And if I understand, also you will have something like 6 actuators, but you say that you will use these actuators remotely. They will be outside of the pipe.
Yeah, exactly. The motors will not be, integrated with the robot assembly, but the idea is to use it from externally, because if we mount the robot, they add unnecessary loading. That's one thing. So the idea is to transfer once again information through cables. So as I said earlier, we are once again, drop into the pond of, the cable management issues. So to address that again, once again. Yeah.
Okay. And why you choose to have this kind of 6 actuators outside and the other ones inside?
No, because for the Caterpillar module, it's because the leg mechanisms has to be coupled with the motors, because we have the spindle screw along with which is the output we'll be using. So that's the main reason the motors of the Caterpillar module are always inside. But however, if we also put inside the motors of the entire architecture must be revisited to accommodate these motors as well. So that's the reason to have the motors of the Caterpillar modules inside and for the tensegrity mechanism outside, because we just need the cables and not the motors as well at the same moment for the actuation of the tensegrity mechanism.
Okay.
Yeah.
And okay, so for this tensegrity mechanism, there are 2, let's say, ways of using it. The first way is to let it in close to a nominal position and do, let's say, and be able to adapt if there is a small change. And the second active one is to pre-configure it for turning of 90 degrees or 45 degrees, just to find a good way, a good path in crossing of pipes.
Yes.
Yeah, something like this. So you will have cable in the springs, and you will pull on the cables in active mode. But in passive mode, you must release the cable and let them and let the spring take the good lengths by themselves. So in one way, the cable, let's say, can retract or not bend, but okay, not be in tension. And in the other way, it will have to be in tension. So you will have to release it from the motor or from the actuator. How you think you will manage that? Because it's strange for me how mechanically you switch from one mode to another one.
To be frank, this investigation was not taken into account, but yes, it was pretty sure it is a challenge, because the first idea was to make the prototype and test it inside a 90-degree pipe without actuation of tensegrity mechanisms. But for the final application, as you said, we will have the presence of cables, and we will never know like what kind of profile it's going to enter. So first, if it's going to be a junction or a T-union, as I said, we can use the cables to actuate them. But in the case of passive mode, for the moment, we did not think about, really retracting or, remove out the connection between the tensegrity mechanisms and the cable. Maybe this investigation has to be done. And one thing maybe might sound weird. For the moment, we used, a motor with very high reduction. So probably it's not that easy to, under static modes, we cannot really turn the shafts of the motor. But what we can do is when the robot is being put inside the pipeline, we should ensure at the beginning, like there is a tightness along each cable, and we just put, connect it to the motor shafts. And maybe if we go for like low velocity or low reduction ratios under no load conditions, the motor can have the ability to to have the rotation. It's not a good idea, because we will not have the the exact bending, because still there exists some inertia of the gear reduction and stuff. So this issue must be really addressed into the future, actually. But
okay. Just another question about.
Une dernière question, s'il te plaît.
Yeah, just one question about the tensegrity system. Let's say in the case with 4 springs, you put I don't understand if you put the springs aligned with the axis 2 by 2, or if they are 45 degrees from the axis of the universal joint.
You mean the positioning?
Or if you have tested both.
You're saying about the positioning of the springs, or?
Yeah, on the top view, you can see the U joint and the axis.
Mm-hmm.
And the springs are located aligned with the axis, and or they are at 45 degrees. And have you tested both of them? I have the impression they are aligned with the axis of the U joint.
It's kind of parallel with the axis of the center. I mean, at the home post, yes, it's parallel.
Yeah. And why this choice instead of turning them off by 45 degrees to be?
No. So basically, the geometric arrangement is like, for example, in the case of 3 SPSU, even at the home post, all the springs are parallel along with the axis of the universal joint, and it's like if you go by the circular law, we have a spacing of 120 degrees between each spring.
You did not optimize the position of the spring by rotating the springs regarding the universal joint. You already say that that's the best position.
Yeah, kind of, yeah. But the thing is, when it comes to the final, assembly with the robot, this mechanism can have any orientation. For example, it can be, we have two. For example, if we have the planar projection, we can see 2 springs parallel to the orthographic projection, or maybe it is just how to say, we can have another orientation where the 2 springs are not exactly the orthographic projection, but at some angle. So it's purely affected by the orientation of the mechanism about its own axis.
Okay, thank you, Swaminath.
You're welcome.
So thank you, Olivier. It's my turn now. As you know, I'm not really competent in robotics. My background is more about biomechanics. Okay. And as your title mentioned, a view-inspired robot, I would like to maybe just do a short comeback to biology, and because I think that the link between robots as a mechanical demonstrator is really interesting to understand also the biological functions. And you did the demonstration, for example, that with 3 or 4 units, you obtained approximately the same capacity or mobility, except in terms of speed. And I think the fourth component system is more interesting for biologists, because it is the equivalent of 4 muscle groups corresponding to front, back, and both sides. And we may have some interesting cooperation to do between the both systems. And I had a question, because I don't really understood if your algorithm and equation integrate weights. So is your robot able to locate itself regarding the gravity?
As in, you're saying that if the robot is able to adjust itself or something, or?
Yes, because when you're looking to animals, they don't act in a similar pattern if they are working or moving against gravity or with gravity or on the horizontal plane. So my question is, when your algorithm integrates weight, is it expected that the coordination of synchronization of the actuator enables the system to move differently depending on these moving against or with gravity?
In the case of the numerical models, for example, in the static, the gravity effects were not considered pretty much okay. So it's just we assumed the self-weight of the robot and stuff. But in the case of experiments, yeah, if you see, for example, and when we have the vertical orientation, we were able to isolate some aspects in the results, like the influences of gravity on the forces of the actuator, for example. And so for example, in the experiments, we just use the leg mechanisms. So it's purely through the contact forces. We were, try to address the issue or to have a better contact with the pipeline walls, be it horizontal or vertical. But when it comes, like as I said, when doing the experiments, we also observed that there are some slight deformations on the leg mechanisms, which could lead to the problem that the robot might slip off, especially when the orientation is vertical. So that's the reason, like the proposal of the 4-bar wheel mechanism, which will be like always ensuring contact with the pipeline walls. And it will be like a supplementary mechanism, which will ensure that the leg mechanisms do not take all the load, but also, the 4-bar wheel mechanisms will also take some of the loading to assure the stability, especially when we are vertical.
Okay. But your concern on the contact for the generation can be synchronized differently. And can you go back to your slide, the 20 one?
Yeah. Okay. Yeah.
If I understand well, here you have the synchronization of the different actuators, and maybe I said that. This synchronization is supposed to be disturbed depending on the orientation of the system.
Yes, of course.
So, did you test it?
Test it as in like we did the experiments for horizontal and vertical orientation, but looking at the graph just like that, significant differences could not be observed, but actually there were some slight differences on the motor torques, especially on the central actuator when the orientation was vertical. And probably it arises due to the effects of gravity. So it was not just through one trial, but maybe 2-3 experimental trials. We found some significant difference. But I mean, it was a bit mentioned in the manuscript, but as a whole, like on a plot, we cannot exactly find a lot of difference between these two data.
Okay, thank you. So it's my last question, and I will ask to Damien to give to us his advice concerning your work.
Okay, thanks you, Pierre. So first, I wish to thank all the jury to be here for a long time for virtual. It's like a virtual conference. I think that we have many comments that. It will be useful for Swami for the future. I have no question to Swaminath because we have passed so many times together during coffee break and different meeting at LS2N. It was a real pleasure to work with Swami. It was very passionate with me. You cannot imagine how many times sometimes I request to him to check to do again some computation or some experiment. It was not so easy also during the last 6 months to exchange all together for the experiment. Could you imagine that when the robot is moving and the nose seems to be not good, how to explain that we have to change something inside the PhD controller or some parameter? For some aspect also, we have planned to make the experiment for 3 motors and 4 motors but unfortunately in the lab we have also many people that they request some part for manufacturing, so we have some delay, we cannot work, so it was not so easy during the last 6 months to do all the experiments that we are scheduling. We have also, I have done also some, for example, I have selected some motors last year. All the computation was not done, but you know that when you want to order some motors, we have some delay and we have to make some shows. So for example, I prefer to have a slow robot with good torque than to have a fast robot but not enough torque. So I have made some shows. But today, I think that Swami was able to show large work from the analytic analysis, kinematics, some aspect for kinematics, for control, and I hope that it will be possible for him in the future to have a good position for research. So thank you again, Swami, for this work, for this presentation, and I have no question.
Thank you.
Pierre, right.
Right. So it's at the end of your presentation and question now, because everybody asked the question you would like to ask to you. So we'll have now to discuss between us. Okay. And so I think that Damien will.
Yes. So we will switch to a virtual room. So if maybe if some people want to ask questions to Swami when we will be away, you can. So see you in a few moments.
Thank you.
So, on est tous là?
Oui.
Swami, I will switch in French for the last thing I have to do now. So, les membres du jury ont discuté de votre présentation. Ils ont tous apprécié et soulevé le caractère pédagogique de votre présentation et de votre mémoire, ainsi que la qualité du travail que vous avez fourni, en soulignant particulièrement le fait que vous avez été capable de vous intéresser à une partie théorique qui était assez complexe et de développer des parties expérimentales tant mécaniques qu'électroniques et numériques de bonne qualité et qui ont abouti à des résultats concluants, dont des publications qui vous permettront, on l'espère, d'aller chercher une qualification, puisqu'il semblerait que ce soit votre souhait. Bien. Donc le jury, à l'unanimité, vous accorde le grade de docteur des universités, non plus des universités là, mais de l'École centrale de Nantes, et vous félicite pour le travail accompli. Voilà.
Merci beaucoup, Pierre.
Félicitations.
Félicitations.
Merci, Chedli.
Congratulations.
Merci, Pierre.
Félicitations.
Merci, Olivier.
Congratulations and felicitations.
Thank you so much, Ramki. Et Margot, merci beaucoup, madame. Et puis Damien, merci beaucoup. Ouais, c'était un plaisir de travailler avec vous. Donc, j'espère qu'on va continuer dans le futur. Et après, thank you everyone, for friends, everyone who participated for my defense. It's a pleasure with all of you being around me. So unfortunately, owing to the COVID, we cannot have the drinks together, but maybe virtually. So take care, everyone, and I hope we will for sure pass a moment sometime in the future. And thanks again.
We can use virtual reality.
Yeah, for sure. Yes.
Merci.
Okay. Congratulations again. And so the best for the future, of course.
Thank you so much, Pierre.
Merci, bonne continuation.
Merci, Chedli. Merci, Damien.
Oui.
Donc,
bientôt, alors.
à bientôt, j'espère, pour de nouvelles réunions, conférences, rencontres.
Ouais.
À bientôt, Damien.
Au mieux.
Merci.
Portez-vous bien tous.
Merci.
Allez,
À bientôt.
à bientôt, tout le monde. Au revoir.
Au
Merci.
revoir à tous.
Thank you, guys.
Félicitations.
Thank you, Lahe.
Congrats, congrats.
Thank you, Emilish. Thank you. Okay, I will probably cut the call. So thank you so much for being present, and we will for sure meet again. I hope once everything is over. So I'll sign out maybe. So until next time, guys. Bye bye.
Bye.
Bye, Lahe. Bye.